This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, the professor for this class, and this is Lecture 65. I'm going to talk about line edge roughness. Several lectures. Another way of thinking about line edge roughness is a stochastic look at the world of lithography. What is line edge roughness? Well, when we print a feature and we think of it as being a smooth line or a space or a contact hole or any such feature, when we actually look at it closely, we find that there's roughness along the edges. And in fact, that roughness is now becoming a large percentage, a large portion of the overall feature size. In the past, the degree of roughness was a very small fraction of our tolerance, how close we wanted the edge to be at a particular place. But now this roughness has stayed essentially constant as our feature sizes have shrank, and as a result the roughness is now taking up a fairly large portion of what we term the CD control budget, the amount we allow the dimensions of our patterns to vary and still get acceptable results. What is this line edge roughness? Well, technically it's simply the deviation of a feature edge from the smooth ideal shape. But really when we're talking about roughness, we're talking about randomness. Random variations that cause the edge to deviate from its desired position. Here I show a top-down view of a line, and you see it kind of wiggles. Both the width is varying and the edge position is varying. And if I look at a cross-sectional view, I see that the side walls are rough. Even the top surface of the photoresist is rough. What causes this random variation? Well, that's what we're going to try to explore, to understand the origins of this roughness and what we might be able to do to reduce it and what its impact on semiconductor manufacturing in particular, but any type of microfabrication. So before trying to explain where this roughness comes from, let's take a very simple example to show why we care. And to look at this, I will pick the simplest structure to understand a gate on an MOS transistor. So here I show a gate. So the kind of light blue rectangle represents a polysilicon gate crossing this purple diffusion region. The gate length is L, the small dimension of the gate width is W. And the gate length and the gate width determine important properties about this transistor, like its switching speed, its current carrying capacity, and the leakage current when we try to turn this transistor off. Errors in the dimension of this gate, as we've already seen, causes disruption in the behavior of this device compared to its ideal behavior. Now, on the right, let's look at a gate that's full of roughness. All right, what do we see here? What's happening? Well, one way to think of it is I can take this gate and break it up into individual slices. So I have a gate here, and essentially I have a whole bunch of transistors in series. So one after the other, after the other, after the other, after the other. And each one will switch a certain amount of current. So, turn on a certain amount when we turn it on. And then all of these are in series with each other. So the roughness, in effect, causes a line width error of one of these little segmented transistors compared to its neighbors. So we have some that are narrower and some that are fatter than they would otherwise be. Well, it's the narrow one that dominates when it comes to leakage current. Because as I make this thing too narrow, I can't turn it off all the way, and so the narrow regions of the gate will have a lot of leakage current. So there are really two ways in which this line edge roughness affects the performance of this transistor. First, no matter what, when you have roughness, you end up with an increase in the leakage current. And that's because the narrow bits allow current to leak. But also, when I take this rough feature and I determine its average line width, the roughness means that sometimes the average line width is a little too big, and sometimes the average line width is a little too small. In other words, the roughness itself has the effect of causing an average line width error. And all the bad things that happen when we have line width errors will also happen here. So we don't like this kind of roughness. It's detrimental to the performance of the device, and as the feature size gets smaller, this detrimental aspect of line edge roughness gets worse and worse. Note that often, instead of talking about line edge roughness, we can speak of line width roughness, which is basically the same thing, except for I look at a variation in the width of the feature as a function of position, and what the standard deviation, for example, of the line width is. You might also notice that the centroid, the center position of this line, is varying with position, so there's actually a center position roughness at work as well. All right, well, we have at least a little bit of idea of why line edge roughness might be something to worry about. Now, what causes line edge roughness? To explain that, let me begin by explaining why we often ignore the phenomenon that cause roughness. We very frequently invoke, often without even speaking it, an approximation, an assumption called the continuum approximation. We know that the real world is discrete. We know that we have atoms and molecules. We know that we have photons for light, for energy, and electromagnetic energy. And we know that we can think about the world in these discrete little packets of matter or energy. But often our science, our chemistry, our laws of physics, our rate equations for chemical reactions, etc., make a continuum approximation. We think about matter and energy with continuous mathematical functions, not discrete mathematical functions. Why? Because it's a heck of a lot easier to deal with continuous mathematical functions. Cosines. We have equations that say the aerial image intensity is this and this, and it has a cosine as a function of x. There's no photon counting going on there. It's a continuum of energy. When we talk about the concentration of the acid generated upon exposure, or the dissolution rate of the photoresist at a particular position, these are all continuum functions. They're not discrete. There's nothing discrete about them. This is the continuum approximation. And it's very useful because it makes life so much easier to think about and to deal with mathematically. But it is an approximation. It ignores the discrete nature of the world. And because of that, using these continuum models of the way the world works, we cannot see things like line edge roughness. We cannot see the discrete nature of the world, and the randomness, not just the discrete nature of the world, but the random component to that discrete nature, which causes random roughness on the edges of our feature. So what do we have to do? We have to rethink the way we talk about the world in lithography, the way we've talked about it so far in this class, in order to include stochastic random variations. In fact, when we think about the world stochastically, we find that the mean value of things like image intensity and acid concentration is the value that we've been talking about before. And we call that the mean field theorem, that the continuum world is equal to the stochastic world in the mean, on average, but not for any given instance of it. Let's take an example. Let's look at chemical concentration. What is the definition of chemical concentration? Well, it's kind of simple. It's the number of atoms or molecules per unit volume. Okay, so if I pick a particular volume and I count the number of atoms in that volume, I will have the concentration, the average number per unit volume. But it is an average, because if I picked, say, a small volume within the larger volume and said how many molecules are in this small volume, it might in fact vary. Unless I have something like a crystal where every atom is in its exact place, then if I pick a small volume and count the number of atoms, I won't always get the same answer. I can get different answers. And this randomness we're about to explore in a moment. But the other important idea here is that we often talk about concentrations and how it varies with position. The concentration of acid as a function of position, X, Y, and Z, let's say. And we talk about the gradient of concentration, which drives diffusion, and all these things. We've used these mathematical formalisms many, many times. But if I say the concentration at the point X, Y, Z, what exactly does that mean? Here's a box, a volume. And if I want to know the concentration, I simply count the number of particles in this box, n of them, maybe it's 22, then divide by the volume of the box, and there's my concentration. But now what if I asked you, what is the concentration at this point in space, where my cursor is pointing right now? Well, the question, when you look at this picture, doesn't really even make sense. Well, I can't really talk about the concentration at a point. Right? If I point to a point in space where there's no atom, then the concentration is 0. If I point to a space here, let's say, where I'm pointing at an atom, well, then I'm pointing at an atom. I mean, it doesn't make any sense to say what's the concentration until I pick a volume over which to average. And yet, we make this fictional statement on what's the concentration at a point X, Y, and Z all the time. Really what we mean is the mean concentration, the average concentration at this point. And if we want to know something more than the average, we have to do a little bit more work. And in fact, what I want to know is not just the mean concentration, the average number of particles within this volume. I want to know what's the variation in the number of particles in that volume. And that's what we're going to figure out right now. And to do that, we will take a stochastic view of chemical concentration. Here's what I'll do. I'll model my atoms or molecules as a point located at its center of mass. Now, this is obviously a reasonably poor approximation because we know all atoms occupy volume. But I'll assume I have dilute solutions. A gas is a perfect example, but even liquids or even solids where the molecule of interest is dilute. They're not that close to each other. So I rarely have two atoms or molecules interfering with each other, where kind of preventing one atom's location prevents another atom from occupying that same space. If I ignore that interaction, then I can model my atoms as being points. Then, if I pick some volume V, and I simply look at a particular atom and ask, is that atom inside the volume or not? Because it's a point, it has to be one or the other. It's either in the volume or it's not. This is a binary proposition. And if you've studied any probability theory, and hopefully you've taken a class in probability, if not, I highly recommend it. It's a fascinating subject with lots of very practical applications like this one. If you've studied probability, you'll know that this question that I'm asking, I have a molecule, is it in the volume, yes or no? That's a binary proposition. Every molecule it has a binary answer, either in the volume or it's not. Yes or no, 1 or 0. And we can describe a collection of binary random variables with a binomial distribution. So let n be the number of molecules in this volume V, and P of n is simply the probability that that's how many I'll find. I might have P of 12 or P of 3 or P of 26. It would be the probability of finding exactly that number of molecules within this volume V. So what is that? Well, we can write down the equation for a binomial distribution given a certain concentration C, that is an average number of molecules per unit volume. Then we can write down the binomial distribution, and here it is in all of its glory with factorials and powers, etc. Kind of ugly, but still not we can work the math and make that happen. Okay? This probability distribution makes some assumptions. As I mentioned before, we assume that the models are ideal points, and that becomes a poor approximation when the concentrations get so high that the molecules get really close to each other. Right? Then the volume excluded by one molecule starts influencing where the other molecule could possibly be. The other thing where this could be a problem is if you have some attraction or repulsion between those molecules, so that the position of one molecule influences the position of the molecules around it. Agglomeration is a good example. Things stick together. But if those phenomena are not going on, then this binary distribution works well. Well, it turns out the binomial distribution becomes, in the limit, a Poisson distribution. And that's good because the Poisson distribution is actually much easier to work with. But it's the same idea. I've got some average concentration C, and then I pick some volume V and I ask what's the probability of finding exactly n particles within this volume V. And it goes by this binomial distribution. You can plug this into Excel or some other, even work it out on your calculator and calculate the probability for any given value of n. Some important properties of the Poisson distribution. First of all, the mean value is C times V. Well, this, of course, makes perfect sense because if it didn't do this, we would be worried about our derivation here, because the definition of concentration is simply the average value of the number of molecules you find per unit volume. So it's we use these triangular brackets to signify the mean value. So that's what this terminology means. The mean value of n is C times V, so C is simply the mean value of n divided by volume, which is almost definitional. So it's a truism. So that worked out just fine. The mean value is exactly what we expected it to be. But this is what you get from having a particular probability distribution associated with the number of particles in this volume, because now we have not only the mean, but the variance. The variance of this number n is also equal to C times V. And this is an important property of the Poisson distribution. It's a distribution where the variance equals the mean. Well, very commonly, we like to think about the relative uncertainty. The relative uncertainty is the standard deviation of a variable divided by the mean value of that variable. And this is probably the most useful way of thinking about this Poisson distribution. The standard deviation of the number of particles you find in some volume V divided by the mean number of particles you find in that volume V is equal to 1 over the square root of the mean number of particles. This the standard result for any Poisson distribution means that if I have a large volume with a large number of particles, the uncertainty, the relative uncertainty, gets very small. So for example, suppose I had 100 particles in a certain volume. Well, 1 over the square of 100 is 0.1. That is 10% uncertainty in the number of particles. I have 100, but sometimes I have 110, or sometimes I have 90. The one standard deviation is 10% of that number. But now what if I had 1,000,000 particles in my volume? Well, now 1 over the square root of 1,000,000 is 1 over 1,000. So not a 10% variation, but a 0.1% variation. Much smaller. Well, what if I had Avogadro's number of particles, right? So if I have these kind of macroscopic sized volumes where I have 10 to the 20 particles, well, 1 over the square root of 10 to the 20 is 1 over 10 to the 10th. That is an incredibly small number, right? Far, far smaller than any measurement error I might have in trying to measure the concentration. In other words, for large volumes, large numbers, the uncertainty, the stochastic uncertainty, becomes negligible. We don't have to worry about it. It only becomes significant when I worry about really small volumes where I have a small number of particles within that volume. then the stochastic uncertainty in the number of particles that you'll actually find in the volume becomes extremely significant. Well, that's the situation that we're dealing with when we talk about nanofabrication. When we talk about lithography at the 20 nanometer, 30 nanometer, even 50 nanometer scale. The volumes of resist, for example, that we worry about are small enough, the number of particles we find in them small enough that we have to worry about this. This phenomenon, by the way, is sometimes called shot noise. And we talk about a shot noise limit whenever we have such a Poisson distribution of particles, and the relative uncertainty in that number goes as 1 over the square root of that number. So let's look at this Poisson distribution. Here is a plot of the Poisson distribution when the mean number of particles in the volume is 9. So here I plot n, the number of atoms per volume, and here's the probability, and you can see there's a very small probability of having 0 and then 1, 2, 3, 4. Notice that the peak occurs at n equal to 9. That kind of makes sense. And 8 is almost as probable as 9. And you see that 7 and 10 are still highly probable. But then when you get far away from the mean value, the probability goes down. So the probability of finding 20 atoms in this volume when the mean number is 9 starts becoming quite small. Another interesting thing, when the mean number of particles in the volume exceeds about 20, this thing starts looking a lot like a Gaussian. Here I show a particular example where I had 42 as the average number of particles in a particular volume. And then I show as in the red line a Gaussian with a mean equal to 42 and a variance equal to 42. And you can see it matches very, very closely with the Poisson distribution. Not exactly, but close enough for most applications. So often we can approximate something like a Poisson distribution with a Gaussian. This is something called the central limit theorem when the number gets large enough. All right, let's use this Poisson distribution for an example. I'm going to take a photoresist as an example, a 193 nanometer resist, and it'll have kind of a typical number of PAGs, the photoacid generator, right? G0 will be the initial PAG concentration in moles per unit volume, let's say. Then I multiply by Avogadro's number, and this gives me a concentration in atoms per unit volume. And a typical number that I got from a particular resist formulation that was pretty standard was 0.042 PAGs per cubic nanometer. Now that's a small volume, a cubic nanometer, right? So you see that the average number is going to be less than 1. But given this concentration, we can figure out what the average number is for any given volume. So if I take a 3 nanometer cube, 3 nanometers on each side, so what's that, 27 cubic nanometers, multiplied 27 by 0.042, and you get the average number in that volume, which is 1.13. So if I go 3 nanometer by 3 nanometer by 3 nanometer cube of resist, on average there's about 1 PAG molecule in that volume. But if I randomly select a volume of this, sometimes I'll get 1, sometimes I'll get 0, sometimes I'll get 2. The relative uncertainty is 94%. So we say that the mean value is 1 plus or minus 94%, which is a high uncertainty. If I make my volume bigger, say 6 nanometers by 6 nanometers by 6 nanometers cube, I find that there are on average 9 PAG molecules within that volume. But there's a relative uncertainty of 33%. So one standard deviation is a third of that. So that's 9 plus or minus 3. Very frequently we'll have 12, or even, it's not unusual to have even 15 PAGs in one volume, whereas another volume might have 6 or 5 or 4 even. This is the stochastic noise. It doesn't come from any phenomenon other than randomness, the random positions of these PAG molecules within the photoresist matrix. You see for 10 by 10 by 10 nanometer cube, the average number is 42. It's the example I picked on the previous slide. And the relative uncertainty is 15%. So even if I pick a fairly large volume on a lithographic scale, 10 nanometers on a side, there's still an uncertainty of 15% just from random variations in the placement of these PAG molecules. Well, 10 nanometers on a side is starting to look like a lithographic feature today. Now, it's still smaller than the lithographic features that we are printing. We're printing more like 20 or 30 nanometer feature sizes. But we're getting close to that, and we're seeing here a 15% variation in the concentration of the PAGs simply due to stochastic noise, shot noise in the chemical concentration. It's starting to become a significant number. Of course, if I have much larger features and much larger average numbers, and this phenomenon becomes less significant. All right, let's look at another example, photons. I won't go through it just like I did for the chemical concentration, but photons follow the same statistics. Every photon is independent of every other photon. If I look at a particular area and say how many photons pass through that area, well, I have some average number, but the exact number follows Poisson statistics. And so we can think about photon shot noise just like chemical concentration shot noise. Let's give you an example. If I have a 193 nanometer resist, and let's say it has a 10 millijoule per square centimeter dose to clear, that is, that's the minimum dose required to make the resist wash away in the development time. That means the exposure dose near the edge of the photoresist feature is about 10. That's a good rule of thumb. Basically, the dose to clear, whatever that dose to clear is for your photoresist, that's about the dose at the feature edge. So if I look at the feature edge, where it's seeing about a 10 millijoule per square centimeter dose, if I think about a 1 nanometer square area, then over the course of that exposure, 97 photons on average will pass through that area and go into the photoresist. That means there's about a 10% variation in the number of photons, so 97 plus or minus 10%. But if I look at this larger volume of 10 nanometers on a side, then I will have 9,700 photons on average, and the photon shot noise will only be 1%. So if we compare this number to the PAG concentration from the previous slide, we see that the 10 nanometer cube had an uncertainty of 15% in terms of the number of PAGs. Here we see an uncertainty of only 1% in the number of photons entering that volume. So you can imagine that the PAG uncertainty will dominate. Note that I'm talking about incident photons here. We could do the same analysis for absorbed photons, and there are certainly going to be less absorbed photons compared to incident photons. As a result, the shot noise will be larger for the absorbed photons. But I'd like to look at another example first, EUV photoresists. For EUV photoresists, we're trying to develop resist with a 10 millijoule per square centimeter dose to size, and that means the resist will have something like a 5 millijoule per square centimeter dose to clear. In that case, a 1 nanometer square area only sees 3 photons. One of the reasons for this big difference is that EUV photons are 14 times more energetic than 193 nanometer light. EUV photons, each photon has 14 times more energy than a single photon of 193 nanometer light. As a result, for the same dose, we have much fewer photons, 14 times fewer photons, as a matter of fact, for EUV light compared to 193 nanometer light. And therefore, the shot noise statistics get much worse. If I look at a 10 nanometer square area, 10 nanometer by 10 nanometer, and I ask how many photons are incident on that with a 5 millijoule per square centimeter dose, well, that's only 300 photons. And those 300 photons will have a shot noise of about 6%, one standard deviation, uncertainty of 6%. Well, that's a pretty big, essentially, exposure dose error. So if I try to expose at this dose, I'm going to guarantee that every 10 nanometer square area will have variations compared to the other 10 nanometer square areas of about 6%. Pretty significant. Pretty significant. And that's going to result in random CD errors as well. All right. There's still more interesting things to discuss when it comes to line edge roughness, but we've looked at one important aspect of the randomness that is inherent in the printing of very, very small things, and that is shot noise. Let's look at what we've learned in Lecture 65. As always, you should be able to easily and quickly answer these questions. If not, please go back and review the material. Define line edge roughness. Explain to me, what is the continuum approximation? Photon and concentration, chemical concentration shot noise follow what probability distribution? And finally, how are the mean and variance related for one particular distribution we discussed, the Poisson distribution? Well, next time we're going to take this shot noise and add other factors to it. Exposure kinetics, post-exposure bake diffusion and reaction, and development eventually to find out how these random stochastic variations result in rough edges. Till then.